Okay, 3.4, velocity and other rates of change. This is part A. Today we're going to do derivatives using basic rules, and we're going to find rates of change, and we're going to find higher order derivatives. Remember, higher order is when you do more than one derivative. Okay, so we're going to start off pretty simple. Find the rate of change of the area A of a circle with respect to its radius. To start off, area of a circle, the formula for that is pi r squared. So they want me to find the rate of change. Whenever you see rate of change, I need you to automatically think derivative. You're going to do the derivative. You're going to find the slope. So, with that said, I'm going to find the derivative of area of a circle with respect to its radius, r. So you know how normally it's dy dx? This is the derivative of y with respect to x. So today, or for this problem, we're going to derive the function, which is area, with respect to its radius. Okay, so dA dr is, now I bring the 2 to the front, right, because you multiply the exponent. The pi was already there, and then the r, and I subtract 1 from the 2, so 2 pi r. So there is the rate of change of area. Interesting tidbit, which is helpful for you to memorize the formulas for area and circumference. So this is area, right? Well, the derivative of area is actually the circumference of a circle. So all you have to do is memorize area and then derive it to find the circumference of the circle. Evaluate the rate of change of A at r equals 5 and at r equals 10. Evaluate. That means plug in, basically. I'm going to figure out what the rate of change is at r equals 5, and then I'm going to figure out what the rate of change is at r equals 10. So 2 times pi times 5, which is 10 pi. This is the derivative with the 5 plugged in. And then 2 times pi times 10, which is 20 pi. Okay, so when they ask you to evaluate at a certain point or a certain value, you're just plugging in. Okay, C. Now notice how they're saying rate of change. They never said derivative. You need to know that. C, if r is measured in inches and a is measured in square inches, what units would be appropriate for dA dr? Okay, so d over dA dr. Now, they're telling me that area is measured in square inches, right? And they're telling me that the radius is measured in inches. So the units, okay, so for area, the units are still inches squared. That didn't change. And then for the radius, the units were just inches. So whatever my answers were, my units will be inches squared over inches. So inches squared over inches, inches squared over inches. Units are important in this class. If you are given units, then you must actually write them. If you were talking about feet, then you need to continue talking about feet. If we were talking seconds, then you need to continue talking seconds. Okay, here's some vocabulary for this section. Average velocity. Average velocity is just basically finding the slope the way you did back in Algebra 1. You have your x values on the bottom, and then you plug them into whatever equation you have to get your y values, and you subtract them on top. But in this class, we're also going to refer to average velocity, or the regular old slope from Algebra 1, as slope of the secant. It's the slope of the secant line. Now this doesn't have anything to do with secant as in trigonometry. Okay, so slope of the secant line. It's not that important in this lesson, but it will be throughout the entire course. You need to know that regular old slope is the secant line. The slope of the secant line. You get 2 points and you find slope. Instantaneous velocity. Sometimes they don't call it instantaneous velocity, they just call it velocity. Velocity is actually the derivative, but we just call it the slope of the tangent as well. But like I said, it is the derivative, the first derivative. Remember, we do have higher order derivatives. And that's the whole really long way to do the derivative, although now we've learned the basic rules and how to do it the short way, the shortcut. Before I go any further, I need you to understand how we're going to write certain things. So this lesson is about particle motion or objects in motion. So we have to have a position. The position function is usually s of t. Sometimes, they'll write it as x of t. Velocity is going to be represented as v of t. And then we have acceleration, and that will be represented by a of t. So position is s of t or x of t. I usually use s of t. Velocity is v of t and acceleration is a of t. Okay, so that's what we're dealing with today. Proceeding with the vocab. Position. Position is simply where an object is. As part of position is displacement, and displacement is a change in position. This should look familiar. S of t2 minus s of t1, because it's the top part of the secant of the slope, or the slope of the secant line. Velocity tells you how fast an object is moving. Not only does it tell you how fast, but it also tells you the direction. Now, if you look back at instantaneous velocity, you'll see that I had v of t. V of t equals ds dt. Velocity is the first derivative. You would derive the position function, s, and get ds dt, and that is velocity. Okay, so if you need to write that for yourself, please do. Velocity is the derivative of position, of the position function. This is math after all. We do use functions. Okay, speed. Speed is the same as velocity, only that it's the absolute value. So speed will never be negative. Velocity can be negative. The negative tells you the direction that the velocity is going, or like usually falling. Speed, however, will always be positive, and that's why it's the absolute value. Acceleration is the rate of change of velocity. So remember, the rate of change means derivative. So acceleration is the derivative of velocity. Therefore, acceleration is actually the second derivative. Okay, so as you can see from what I wrote acceleration is equal to the derivative of velocity, which is equal to the second derivative of position. Example 2, suppose an object has the position given by the function s of t equals t squared minus 6t plus 4. Okay, A, find the displacement during the first 4 seconds. So how much did it travel within the first 4 seconds? The first 4 seconds means I'm going from 0 to 4 seconds, right? So displacement, if you look back on top of your page there, it's basically the position function with a time plugged in minus the position function with the other time plugged in. So I'm going to call this T1 and this T2. And I'm going to plug them into the function, the position function. Okay, so, oh, let me fill these in. T2, T1. All right, so I plug in S of T2, and I get -4. Let me make sure. 4 squared, that's 16, minus 6 times 4, which is 24, plus 4. So yeah, -4. Okay. And then I plug in 0, which is pretty easy. T squared, 0 plugged in is 0, minus 6 times 0, plus 4. Still 4. So -4 minus 4. So my displacement was 8. Okay, now in this problem I don't have any units. Just to make me feel better, let's just write units. I don't know if this was feet, centimeters, whatever. So the displacement of this object, whatever it was, is -8 units. All right, B. Find the average velocity during the first 4 seconds. Okay, so now average velocity. Remember, average velocity is the slope of the secant line. Slope of secant line. That's the good old-fashioned slope that you found back in Algebra 1. So the average velocity. Now remember, displacement was actually the stuff on top. The S of T2 minus S of T1. And then the bottom stuff is basically the times subtracted from one another. So T2 minus T1. We already did the displacement. It was -8. So I'm going to go ahead and plug in -8. I'm going to divide that by the times. Remember, the times were from 0 to 4. It still says first 4 seconds. Okay, just like the first question or problem. So I'm going to plug in the 4 and the -0. I get -8 over 4, which is -2. So the average velocity was 2, and like I said, we don't have units, 2 units per second, because the time here is in seconds. Okay, C. Find the instantaneous velocity. Okay, so you're like, oh my god, they're just asking me for velocity, velocity, velocity. So displacement was basically how much it moved. B, average velocity, that's the old kind of way of doing the secant, the slope. And C, instantaneous, that means at this time. I don't have 2 points, I just have 1. So this is the derivative. So I'm going to derive my position function. And then I'm going to plug in 4. And that'll be the velocity, the instantaneous velocity at that point, at that time, at t equals 4 seconds. Not from 0 to 4 seconds, not that interval, just at 4 seconds. Okay, so the function was, let me write it down. So now I need to derive this. So the derivative is going to be my velocity. So s prime of t is my velocity. So let's see. Bring the 2 to the front, then t minus 1. Okay, minus 6t. That becomes just 6. And there's my function. Well, let me go ahead and plug in the 4. You get 2 times 4 minus 6. So that's 8 minus 6. So that's 2. My instantaneous velocity is 2 units. Again, I don't know what my thing is. 2 units per second. At the time 4 seconds, the velocity was 2 units per second. Okay, D, find the acceleration. Okay, so acceleration is the second derivative of the position function, or first derivative of velocity. So acceleration, oopsie, acceleration is equal to velocity's derivative, which is equal to the second derivative of the position function. Okay, so to find acceleration, I'm going to derive my velocity. My velocity was up here. This is my velocity function. So I have to derive that. So let's see, 2t minus 6, if I derive that, I just get 2. This will be my acceleration. 2 units, whatever they are, per second squared. Acceleration is always squared. So this was our first round with velocity, position, and acceleration. Okay, vertical motion. Vertical is up, down. Example 3. At time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. You should have a picture on your notes. The position of the diver is given by s of t equals negative 16t squared plus 16t plus 32, where s is measured in feet and t is measured in seconds. This time we definitely have units. So A, when does the diver hit the water? Okay, so when. That means we're looking for the time, t. Okay, so I'm looking for t. I need to figure out what kind of equation I need. What does it need to equal? In order to figure out the time when the diver hit the water. Okay, so I wrote a little note there. Basically what we're doing here is we're finding the time when the position is 0. The position is 0 when the diver actually hits the water. Okay, so we're going to take our function and we're going to set it to 0. I'm going to write that down. Now my job is to figure out what t is. This is a quadratic equation, so best thing to do when we set it equal to 0 is to factor. I do see that these numbers all have a great common factor of 16, and actually this negative in the front I can actually I can also get rid of that. So I'm going to pull out a negative 16. Alright, so I'm pulling out the negative 16 and I'm left with t squared minus t minus 2 on the inside. Alright, so now I need to factor. I need two numbers that multiply up to negative 2 and add up to negative 1. So I have t plus 1 and t minus 2. So now I solve using the zero product property. And if you don't remember the zero product property, that's if something multiplied by something else equals 0, then one of these three somethings must actually be 0. Since we don't know which one of them is, we make them all 0. That's the zero product property. So here I use my zero product property and I got two answers. T equals negative 1 and t equals 2. Now one of these don't make sense. Now if I look back at the question, at time of 0 seconds is when the diver jumped. So at negative 1, he wasn't jumping. So this one makes no sense. So the time when this diver is going to hit the water is t equals 2 seconds. So I have the diver hits the water at t equals 2 seconds. Please write that down. It's important to know how to write what's happening or what you're solving for in the problem, rather than just giving me t equals 2 seconds, you need to be able to explain what are these 2 seconds. That's when the diver hits the water. All right, next up, B. What is the diver's velocity and impact? Okay, so what I'm trying to do is I'm trying to figure out how fast he was going at the time that he hit the water. Okay, so I wrote what we're doing. I need to figure out the velocity. It's the derivative. So we're going to find the derivative and plug it in, and plug in t equals 2, the 2 minutes that we got, or sorry, the 2 seconds that we got from A, because that's the time that he hits the water. We need to figure out how fast he was going. So we're going to derive. Velocity is the derivative of position. So I get negative 32t plus 16. This is my derivative. So now I'm going to plug in the 2 seconds. Negative 32 times 2 plus 16. So that's negative 64 plus 16, which is negative 48 feet per second. That's how fast he was going. Notice the negative 80, or sorry, the negative 48. That's because he was falling. He was coming down, right? You don't jump up into a pool, you jump down into a pool. So the diver's velocity at impact is negative 48 feet per second. Okay, example 4. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s equals 160t minus 16t squared feet after t seconds. A. How high does the rock go? Okay, so in order to figure out how high the rock goes, I need to focus on the fact that an object reaches maximum height when the velocity is 0, because it stops going faster, right? It stops speeding up once it reaches its height, because then it comes right back down. So I'm going to go ahead and write that. Okay, so I have my position function, and I decided to call it s of t. In the question it's just s, no biggie. So remember, objects reach maximum height when velocity is 0. I want to know how high the rock went. So in order to figure out how high it went, I need to figure out the time that it got there. Because if I know the time, then all I have to do is plug in the time here, and it'll give me the position, how high it went. But I don't know the time. So I'm going to use velocity to figure out the time that it reached its height, its maximum height. So I'm going to derive. So here's the derivative. Now I'm going to set the derivative equal to 0. Now I'm going to solve this for t. I'm going to try to figure out when is this time that this rock gets all the way to its maximum height. Alright, so subtract 160 from both sides, and I get negative 32t equals negative 160. And now I'm going to divide both sides by negative 32, divide by negative 32, and I'm going to get t equals positive 5. These are in seconds. So at 5 seconds, this rock reached its maximum height. So at t equals 5, the rock reaches its highest position. Now I actually have to find where is this position? How high does the rock go? So I'm going to use the position function, which is s of t. Let's see, s of t equals 160t minus 16t squared. And I'm going to plug in my 5 seconds into my function, my position function. And that should tell me the height, which is the highest height that the rock reached. Yeah. So I plugged in the 5s, and I get 800 here minus 400. So 400 feet is the position. So the rock's maximum height is 400 feet. So that's how high the rock goes. The rock's maximum height is 400 feet. That's how high it goes. Okay, so B, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up. And then it asks for on the way down. Okay, so 256 feet above. What they're giving me here is the position. So they're telling me what the position equals. It's 256 feet. So my job is to find the velocity and the speed. Well, let's take velocity because speed is basically the same thing. So velocity, in order to find velocity, I can derive the position function. And all I really need is the time. I plug in the time and I get my velocity. Well, right now all I have is the position. So I'm going to take the position function and I'm going to set it equal to the 256 feet. And that's going to allow me to figure out the time that it took after how many seconds for this rock to reach 256 feet. Best way to do this is to subtract 256 from both sides, and I end up with an equation that equals 0. And that's good because then I can factor this. Now, I see that they have a common factor of 16, so I'm going to pull that out. And I'm left with, well, actually, let me rearrange this. Hold on. Okay, so I have this negative 16t squared. Usually when we factor, the squared part is at the beginning. So I'm not digging the negative. So what I'm going to do is I'm going to psych this equation out. And what I'm going to do is, instead of subtracting the 256, let me go ahead and subtract the 160 and add the 16t squared to the other side. So I'm going to subtract this, and I'm going to add this to the other side. So now I end up with 16t squared, totally positive, minus 160t plus 256. And now the left side is just 0 because I got it rid of everything that was there. I like this better. Now I'm going to factor. They do have a common factor of 16. So I get t squared minus 10t plus 16. Now I'm going to factor this. I need two numbers that multiply up to 16 but add up to negative 10, and that's negative 8 and negative 2. I'm going to use the zero product property to figure out what my two t values are. So I get t equals 8 and t equals 2. Now, I have two times because this object did reach 256 feet twice. Once on its way up and once on its way down. So I have my two times at which the position was 256 feet. Like I said, one on the way up, one on the way down. So what I'm going to do is I'm trying to find the velocity and the speed. So I'm going to need the velocity function. Remember, velocity is just the derivative of the position function. So velocity is going to be 160 minus 32t. And what I'm going to do is I'm going to plug in my times, my 2 seconds and my 8 seconds. So plug in my 2 seconds, and I'm going to plug in my 8 seconds. So when I plug in the 2, I get 96 feet per second. And when I plug in the 8, I get negative 96 feet per second. Oops, forgot the t. 96 feet per second. Now notice the negative because that's on the way down. Negative means down. Okay, so there are my velocities. Now speed. I can't forget about speed. Speed was there. It said, what is the velocity and speed? Remember, speed is the absolute value. So for t equals 2 seconds, the speed was 96 feet per second. It's the same as velocity. For t equals 8, the speed was 96 feet per second. It's still the same. It's just I don't get to make it negative because speed is positive. So I'm just going to write At both instants, speed is 96 feet per second. C. What is the acceleration of the rock at any time t during its flight after the blast? Okay, acceleration. It's asking me for the acceleration. In order to find acceleration, you're supposed to take the position function and derive it and get velocity, and then derive that, and you're supposed to get acceleration. So, acceleration is the derivative of the velocity, or the second derivative of position, however you want to look at it. The 160 becomes 0, and the minus 32t becomes negative 32. And so my acceleration is negative 32 feet, because we're talking about feet, per second squared. Because remember, this is a rate of a rate, seconds squared. Okay, D. All right, D. When does the rock hit the ground? How long was the rock aloft? Okay, so one question at a time, even though they're both the same, basically. When does the rock hit the ground? The rock hits the ground when the position is 0 again. So position is 0 when it starts off, being propelled into the air. And then when it hits the ground again, the position is 0 again. So we're going to take the position function and set it equal to 0. Okay, so I'm going to find the time, the t value, for when my position function is equal to 0. So I'm going to set it equal to 0, and then I'm going to solve for t. So I get 160, or sorry, I can pull out 16 from both of these numbers. So I get 16 from here is 10t. Actually, I can pull out 16t. I'm not paying attention to what I'm doing. 16t. They both have that factor in common. So I end up with t, or 10, holy crap, minus t equals 0. Then I do the zero product property. Something times something equals 0. One of these must be 0, so we make them both equal 0 and figure out what they are. So 10 minus t equals 0. So basically I get t equals 10. Okay, and then on this side I get t equals 0. So let's see. T equals 0. That's the initial time. That's when the rock was propelled. So that was at the beginning. T equals 10. This is when it hit the ground. So it asks, when does the rock hit the ground? The rock hits the ground at t equals 10 seconds. It says how long was the rock aloft? Basically, how long was the rock up in the air? Let's see. Up in the air. And like I said, it's the same answer. It's kind of the same answer. It was in the air for 10 seconds. Okay, the rock hit the ground at t equals 10 seconds. Therefore, the rock was aloft for 10 seconds. And that's it. Do your homework.